Okay, so John's going to talk to us today about locally dualizable modules.
Thank you. I have to say I've never used one of these projectors before, so you will have to put up with my inexperience. But I did something to my shoulder. I was going to give a board talk, but then I did something to my shoulder, and it will not make it through an hour of writing on the blackboard. So I've scribbled these out this morning. So I'm going to start off by giving you the sort of the full, what you might call abstract way of doing this. The abstractions go like this. I want to take a tensor triangulated category and probably compactly generated. There are probably some more things you go through in, but generally I only deal with nice things. So figure that they're really reasonably nice. I want you to be a localizing tensor ideal in C. What localizing means is that it's closed under arbitrary direct sums, coproducts, as it were. This is a surprisingly stringent condition. I would not have believed that this would actually have so much implications years ago, but it's actually surprisingly stringent. A tensor ideal means that it's triangulated with the same triangles. It's a full subcategory, and it has this property that if I take any x in the large category and any y in the small category, then the tensor product is in the subcategory. Okay. Now, when we've got this, what we have here is we have two functors. What we call a localizing functor, which takes f into the quotient category, the Vernier quotient, or Bell's field quotient, if you like. And what that does is it inverts. It's the same objects, but it inverts any morphisms if the third object in the triangle of that morphism is in the subcategory. There's another category, the co-localizing category, or sometimes called local cohomology functor. Local cohomology functor, which takes G back to U itself, which is the category. And so we've got these two functors. For any x in the large category, we have a triangle that goes from g of x to f of x. So it goes from an object in the subcategory to the object x to the something in the localized category. And these are idempotent functors in the sense that if you apply them twice, you get the same thing as if you applied it once. So, in other words, G composed with G is G, and F composed with F is F. And strangely enough, if you apply G to F, you get 0. Okay, in this particular case. Okay, so that's the situation. All right, so the
Sorry, wait, should G be going from U into C? Or is that?
No, G is going from C into U, actually. Okay, and I'm going to give you some examples of these, and you will see sort of how this goes in a way. But I thought I'd write down all this abstract stuff first.
There's another question.
I would also want to ask a question.
Yeah.
When you form this quotient, so do you only invert the morphisms if the code of that morphism is in U, or what do you mean if the third object?
Well, every morphism fits into a triangle, and so if the third object of that triangle is in the subcategory, then you invert the morphism.
Okay.
That's the way it fits. So you invert the morphism if the third object of the triangle of that morphism is in there. Okay, so what do we want to do? All right. Other word in my title is dualizable. An object is dualizable if you have this isomorphism. if this map is an isomorphism. And what this script harm is something called the internal function object in the category C, and this is something that you get out of Brown's representability theorem. You apply Brown's representability theorem, and this is sort of the thing that this is sort of the thing that comes up that gives you the representation. So as I say, there's this internal function. As I say, I'll give you examples of this in a minute. One of the consequences of dualizability means that if X is dualizable, then you get these. Then you get this. Get an isomorphism here, and again, that's the harm. The internal harm. Okay. So let's see. So what do we learn? Okay. All right. So I'm going to write a sub C. Sorry about the script here. I want that to be the subcategory of compact objects in C. An object is compact if harm of that object into anything commutes with arbitrary coproducts, direct sums. In this particular case.
So are they set index coproducts?
What now?
Set index coproducts? Set index coproducts.
Yes, I guess that's right. Set index coproducts. Yeah. Okay. As I say, I don't deal with any categories, so you can't do that with them. Okay, and what we know is that that this functor G, which takes the category C back to U. All right, this is the colocalizing functor that the image of that of a compact object is dualizable. That is dualizable in U, and also direct summands of that are also dualizable. And so the question that came up is this everything? Can you, in other words, is this functor G in some sense surjective? Now you have to allow direct sums, and that in fact, when you're actually thinking about this problem, becomes just complicates things considerably, because whereas you might be able to write down something that you know doesn't come from a compact object, it's very hard to figure out whether or not it might be the direct summand of something that comes from a compact object. So the question is this subcategory of dualizable objects equal to the idempotent completion? That means you throw in direct summands of this image of the compact objects. Year and a half ago, I spent 2 months in Bonn at the Hausdorff Institute, and this was one of the questions that we came upon. And what made this sort of more interesting was the fact that some reasonably well-known young person had a proof that it was true. That is, that the answer was yes to this. It turned out that the proof fell apart. I'm not going to mention any names here, but the proof fell apart. But it didn't mean that they had a counterexample. It meant that just there was something wrong with the proof. So this was something that got discussed. I didn't believe that it was true. I know Dave Benson didn't believe it was true. Several other people didn't too, but we didn't have a counterexample or anything. So that's really what this talk is about, is trying to address this one issue. Okay, now let's get specific. That is as specific as I get. I'm going to talk about group algebra. So we want G to be a finite group, and K, let's say algebraically closed field of characteristic P. The algebraic closure actually just saves you a lot of words. in this. It's not really necessary. The category we want is the stable module category. So this is the category whose objects are all KG modules. I mean all of them. I mean, you know, infinitely generated and everything. The morphisms are given by, well, what do you want to do? We want to factor out projective modules is what it amounts to. And so the way you do this is you take the morphisms from M to N and you factor out those that factor through a projective module. Now, if you've got a projective module, the zero morphism will factor through it. And so that means that this is an isomorphism now. Let's put it that way. The identity homomorphism on a projective module is then equal to the zero homomorphism, and consequently the projective module is equivalent to the zero object in this category. So this is what we want to look at. We can say what the compact objects are. Compact objects are really just the finitely generated modules. So these are the ones we usually think of, but you know, those are the compact objects in this particular case. Those are the only ones whose HOM of that into something will actually preserve direct sums. Preserve arbitrary direct sums, or set indexed direct sums. The localizing tensor ideals have been classified. It was sort of along the lines of the same classification that we got for tensor ideals among the compact objects. This was done by Benson, Iyengar, and Carlson a few years back. And basically, what we want is subsets. They're classified by subsets of the support variety, which is basically homeomorphic to the proj of the cohomology ring. That is, the proj of the cohomology ring is the collection of all homogeneous prime ideals with the Zariski topology of it. Okay. And so what this says is, if you've got a localizing tensor ideal, then there has to exist some subset of this V sub G of K, which is the spectrum of the proj of the cohomology ring, such that U is the set of all modules whose support variety is in V. Now let me explain this a little bit more.
Sorry, John, I didn't catch, so is G a finite group or finite group scheme?
I'm just doing finite group.
Okay, so for finite group schemes, the same term holds.
Yeah.
And there's a big stratification result by Benson, Iyengar, Krause, and Pitsover, is that correct?
Yeah, I think that's correct. Yeah.
And it'll
That's
fall
done
out,
it.
it'll fall
Well,
out.
this probably, but in the case that I'm going to do this, I really don't think it makes much difference.
Okay.
Because I'm going to do it for elementary abelian groups, and that's you know, a lot of the cohomology, even for the group schemes, finite group schemes, comes down to elementary abelian groups.
Okay.
So it's not really going to make that much difference. Okay, so this is the story. Now what do these things mean? Let me go through this real quick. But I want to do it in a specific context because you'll be able to see how a lot of this works. So here's the example I want to take. I'm going to assume P is equal to 2. I'm going to take G to be an elementary abelian group of order 8. So generated by X, Y, and Z. So this means X squared, Y squared, and Z squared are all 1. All right, so this is an abelian group, and all elements have order, all non-identity elements have order 2. So I'll do a little bit of playing around with symbols here. Let me let cap X be X minus 1 or X plus 1, since it's very characteristic too. Cap Y be Y minus 1 and cap C be Z minus 1. What you should notice is that if I square x minus 1, I get x squared, which is 1, minus 2x, minus 2x, minus 1. But 2x is 0, the 2 is 0, and the x squared is 1, so what you're going to get is you're going to get 0. So x squared, y squared, and z squared are all 0. And in fact, you can write down what the cohomology, what the group algebra looks like. It is this truncated polynomial ring, where the with this ideal factored up. Okay. Now here's your definition of. Here's one definition of the support variety. Okay. So for M of kg module, I'm going to let v sub g of m be the set of all points in this case. In this case, this proj was actually a copy of P2, projective 2 space. Okay, so I take a point in there, alpha, beta, gamma. It is in v sub g of m, provided this element u, which I write as 1 plus alpha x plus beta y plus gamma z, does not act freely on m. Now you can check, by the way, that u squared is equal to what? That u squared is equal to 1. So this generates a subgroup of the group of units of the group algebra of order 2. And so what we're saying here is that this point is contained in v sub g of m, provided when you restrict m to that action, the matrix basically doesn't break down into a direct sum of blocks, of 2 by 2 blocks, basically. That's what that amounts to. Okay? And now what happens here, what the classification says, is that if I've got V, which is some subset of V sub g of k. The V sub g of k, of course, is going to be the entire projective plane, the entire projective 2 space. Well, if V is some subset of that, and U is the set of all modules with V sub g of m contained in V, then this U is one of these localizing thick tensor ideals. And vice versa. If you've got a localizing thick tensor ideal, then you have some subset V that with this condition. Okay. All right. So now for under the circumstances of those functors, okay. So G was the co-localizing functor. If X is actually contained in U, then G of U actually fixes it. Now for X, any element in here.
X equals X, what isomer to X, you say for X is equal to U, and then the conclusion of your sentence doesn't have anything about X in it, so should that be G of the X is isomer to X?
Oh, I wrote the wrong thing. It should be G of X equals X. Thank you. Yes. It should say G of X equals X. Sorry. For X in any object in the stable module category, we have this triangle. And this is in fact that localizing triangle that I was talking about earlier. Okay. So it goes from G of X to F of X. And what you know is that the variety of G of X is actually contained in this set V, in this particular case. Okay?
What is the functor G of X?
It is, well, I'm going to tell you in just a minute.
Okay.
Okay? Okay? I mean, it's actually given quite nicely. Okay. So, well, we've got a similar triangle for the trivial object. And the trivial object, I'm going to give these things special names. This is E of U. That's the that's an element in the subcategory U, and this is F of U. These are idempotent modules, in the sense that if I take E of U and tensor it with itself, I get E of U back. I mean, plus projectives, you know. but I throw away the projectors. It's equivalent to E of U. Same thing with F of U. And we also have the property that if I tensor E of U with F of U, I get a projective module, which means it's zero in this category. Okay. So what happens is that B sub G of U is actually of the E of U, that's the G of K, is actually V, and B sub G of the F is the complement of V. It is all points not in V. Okay. So what happens is G of X is we can actually get in the following form. If you take G of X, it's just X tensor with this E of U. Okay? And F of X is X tensor with the F of U. So these idempotent modules give you the idempotent functor. Idempotent functors that we're interested in. Okay? So now also in this case, this internal hum, didn't say anything about that, but this internal hum is just the ordinary hum over the field, over the base field, K. All right? And we note that hum of Mn is a module that it is an actual object in the stable category, or in a module. And the way you do it is if you've got F contained in hum K Mn, then for any G, what you do basically is you just conjugate by G. You think of it as a matrix. Well, it's only a matrix, of course, if it's finite dimensional. But you know, that's basically what it is. Okay. So what's the dual? Well, the dual is the usual thing. It's just homomorphisms of M into the base field. Okay. It's what you would expect. But something funny happens here. And that is if M is in U, then this thing is actually isomorphic to this. Oh, and I've left something out. I should put underbars on that. Because I want these to be hums in the stable category. Okay. All right. So this is basically what you get. And actually this is wrong. This should be without, but this should be okay. Now why is this true? Well, the point is, if M is in U, then if I map M into K, and I compose with the map from M into F of, if I compose with the map from M into F of K, because the support varieties do not intersect, that map has to be zero. And therefore, by the triangle, that map has to factor through G of K, which is this E of U. Okay, so this is what you get. So we're going to get this, that these two things are equal. And if we let U of D of U be the subcategory of dualizable objects, and I want to emphasize, I mean dualizable objects in U. Okay, so they're dualizable in U. They may not be dualizable in the whole thing. Okay, if you let that be the subcategory, then this question comes down to this: is this D of U the idempotent completion of this ST mod tensor E of U? Because this is the image of the compact objects, the little ST mod. This is the finitely generated modules that I'm going to tensor with this E of U. Okay. And I will note, this is something that you just proved, not too hard, is that D of U is a triangulated thick subcategory of U. It's closed under direct summands, and it is triangulated. Okay, so let's see, so where are we? Okay, let's get back to the example. All right, so this is the example where we've got this elementary abelian group of order 8. And p equals 2. Now what I want to do here is say that, well, we can make some progress here because of the fact that in certain cases we actually know what this E of u looks like. So I'm going to actually write this down. And I think actually at some earlier talk in this seminar, I actually talked about this. So, but you know, so you may be seeing something that you've seen before. All right. So I'm going to take KH to be the subgroup generated by just X and Y, and so H is the subgroup generated by X and Y. So KH is this truncated polynomial ring again. Okay. And I want to take a particular point. I will take the point V to be the subvariety consisting of the single point 0, 0, 1. So an element in the subcategory with this variety associated to this subvariety is a set of all things that are basically not free on Z, but free on every other combination of not free on 1 plus Z, but free on every other sort of linear combination of alpha X, of X, Y, and Z. Okay? All right. Now, here's the way you construct this E of U. You let P epsilon be a minimal predictive resolution. Okay. It's a KH projective resolution of K. So the terms P sub I are free KH modules. The resolution looks like this. Now we want to take E of U. What we want to do is I want to add up all the terms. Just going to take the direct sum of all the terms of that. Now, it's clear what the action of H on this is. So we know how X and Y act. All we have to know is how Z acts. Well, capital Z has the property that its square is 0. So I need something whose square is 0. Well, let me just take the boundary map. Boundary is 0. It's a resolution. Right? So I'll let Z act as the boundary map. And then this gives me a module, this gives me a KG module. And it turns out with some effort you can prove that this is in fact exactly what you want. The Z does not act freely on this, only because, I mean, this is all exact up to here, but it's not exact at that term. This sequence is not exact at that term. So when I cut off the K, it's no longer exact. So that's why Z does not act freely on this. Okay, so this is what I'm looking at. Now, what I want to find out is what is the endomorphism ring of this E of U. Okay, so I've got a projective resolution. I want a map of projective resolutions. And it's got to commute with Z, which is the boundary map. It's got to commute with X and Y because it's a map of the projective resolution.
So is this a colimit of a construction then for the E of U? So you pick this sequence.
No, I think you can just take a plain flat out direct sum. I don't think you need a colimit.
Okay.
I mean, you could make it a colimit, but
Yeah, I was just
but
wondering.
I think, I mean, you know, it's just an infinite Cartesian product, you know.
Okay.
Yeah. So anyway, so where was it? Okay, yeah. So what you've got is you've got a chain map between two projective resolutions. Okay. Now, chain maps actually correspond to elements of cohomology. So if I've got a chain map, let's see, let me push that up. if I've got a chain map, or if I start with an element of cohomology, then what happens? All right, if it's in degree n, then it would be a map that would be represented by a cocycle from Pn to K. Actually, uniquely, this would lift to a chain map on the projective resolutions. And in fact, all of the homomorphisms from E of U to itself have this form, or they're sums of things in this form. Okay, so you better watch out. You can't add them up. But this is where you start, is with all these chain maps, and they come from elements of the cohomology of H with coefficients in K. And I might point out, okay, that if you have two different chain maps that are homotopic, then that's going to mean that these things factor through a projective. Okay, and so in the stable category, it's going to be 0. So it really is cohomology classes, not just cochains. Okay, so this is what we get from this. Okay, so what happens? Let me just put this on here. So an element in this endomorphism ring, by the way, when I write the underbar, I mean in the stable category, is a sum of these. And the point is, though, that if you look at how these chain maps work, we can add up, we can take one in each degree and add them all up. I can add up an infinite number of these, because on each term, it's only going to go to a finite number of things. In other words, if I take any Pn here, it will only go to things that are of lower degree. And so I'm not really adding up. So locally, I'm adding up something that's finite. Okay. All right. So I can act. So what we're going to get. So what we're going to get here is not something in the sum of the HIs. It's going to actually be in the direct product of the HIs. Okay. All right. This is the really important part that I want to make here. Okay. So what happens? Well, the punchline of that is that this is actually a complete local noetherian ring. Okay. It's got a unique maximal ideal. That's the stuff that of degree 1 or greater. That's where the zeta 0 is equal to 0. And it's complete because you can actually invert anything that you can actually. It's local because you can actually invert anything that where the zeta 0 is not 0. And the zeta 0 is in Homs. It's in H0, which is just K. Okay, so it's a complete local ring. Okay, and this is really what we want to use here. So we can actually get some information about that. All right. So where does this take us? Let me show you how I want to do an aside now and construct some modules. All right. And the way you construct the modules is as follows. Let's pick an element zeta, which is in this endomorphism ring of U. So again, I think I left that up. Let's put an underbar on that. Okay. This zeta, which is, I didn't mark it. Here's my zeta. Right. This zeta is going to be a map from EU to EU. Consequently, it fits into a triangle. Okay. And the third object in this triangle is something that I'm going to call M sub zeta. And what we want to note about that is that this is in fact a dualizable module. And the reason why you know that is, well, because E of U itself is a dualizable module. It is in fact the image, it is in fact G of K. So that's a dualizable module. And the collection of dualizable modules forms a triangulated subcategory, so that triangle is, by the 2 out of 3 argument, this element is in the, is dualizable. Next thing we want to note is that if I look at HOM of M into EU, this is an AND EU module, again, because I just composed on the left with an endomorphism of EU. The left and EU module. Let me let the annihilator of zeta, let me let the ANN zeta be the annihilator in this ring of this group. Okay. Now this is in and EU, and there's a theorem which is actually not that hard to prove, but the theorem says that this annihilator of zeta is equal to the radical of zeta. It's the set of all things such that some power of it, generated by the set of all things, whose some power of it is actually in the ideal generated by zeta. So I want it to be in the radical of, that should be in the radical of the ideal generated by zeta. So this is what we get out of this. We can say what these things are. All right. Now, having said that, then what we want to do is we want to pull out a little bit of commutative algebra, commutative ring theory. Okay. And what we'll say is we'll let R be a complete local noetherian ring having 12 dimensions at least 2. There are probably some more hypotheses that you want here, but this will be sufficient. But it's basically this. Okay. So this is an old theorem, goes back to 1972 by a guy named Lindsay Birch. And what Lindsay Birch proved was that this ring R has what they call countable prime avoidance. That means if I have any countable collection of proper prime ideals, I can find an element that is not in the union of those. Okay. Now, there's also we also want Kroll's principal ideal theorem, and it's the same hypothesis: R is a complete local ring, Kroll dimension at least 2. It says the maximal ideal of R is the union of the height 1 primes. Height 1 means sort of minimal prime. Okay. So this tells you that if I have any element in R, it is in some height 1 prime. Prime. All right. So what do you get when you put these together? What you get is that the number of height 1 primes must be uncountable. Right? Because I can take all of the ones that I can count, and take any countable set, I can avoid that. I can avoid that. So this is Srikanth and I, by the way, are not the first to use this technique. Actually, this paper by Birch has got lots of citations over the years. But when you put this together, here's what we get in terms of what we were talking about. Well, let's assume that K is countable. Okay? Then I can find an uncountable set W of elements in this endomorphism ring such that if I take any two elements in W that are not equal, then their radicals are different. Okay, now remember the radical of the ideal that they generated different. The radicals were in fact the annihilators of these modules m zeta. Radical zeta was the annihilator of the module m zeta. So what it means is that, put another way, is that there are an uncountable number of isomorphism classes of modules of the form m zeta. Okay, now these are all dualizable modules in this ideal. So what we want to do is we want to do one more calculation here, and that is what we want to note is that if you've got a countable field, then the number of isomorphism classes of indecomposable KT modules is countable. That is indecomposable, and I should have said finite dimensional. Right. Yeah, indecomposable finite dimensional KG modules is countable. And the reason for this is really pretty straightforward. I mean, if I look at all modules of dimension n, for example, all I have to do is to make a module out of it is to find an action of the generators of the group. To define an action, even by picking a basis, all I have to do is say what a matrix for that thing is. There are only a finite number of matrix entries.
Mhm.
Okay? There are only a finite number of generators. There are only a finite number of things that you have to pick out to define that module. And so for modules of dimension n, they're going to, if you've got a countable field,
Mhm.
they're going to be only a countable number of modules of dimension n. And now, okay, well, there are only a finite number. There are only a countable number of dimensions, so you can use the usual trick, to prove that this is in fact countable. Okay. The other thing you can say is if M is in ST mod, that is, if it's finitely generated, then the number of indecomposable summands of this tensor product is finite. And the reason is because this thing is going to have the endomorphism ring of that module is going to have an action, is going to be finitely generated as a module over the endomorphism ring of E of U. And consequently, there can only be a finite number of idempotents in that endomorphism ring. So it can't have too many direct summands. Only a finite number of direct summands. So this is what we've got. So on the one hand, if you've got this, which is basically generating the image of this G functor, this co-localizing functor, there are only a countable number of objects in there, even when counting direct summands. But on the other hand, we had an infinite number of modules, these modules m zeta, which were also dualizable. So the theorem that you get, basically, put succinctly, is that the answer to the question is no. Okay, in this particular case. Okay. So this is basically what I want to talk about. Let me add a few things to it. We can extend this to any finite group. I mean, I'm doing this for a group of elementary abelian group of order 8. We can extend this to any finite group, any P, provided the group has a elementary abelian subgroup of rank at least 3. That is, of order P cubed or greater. So it's got to have an elementary abelian subgroup of rank at least 3. And then the same thing happens. We can also do this for the derived category of a ring R, where R is a countable commutative noetherian. And it's basically the same idea. It uses a whole bunch of other machinery, but we use machinery from the commutative algebra. But it's basically the same thing. As you use this Lindsay-Birch theorem to get that there are uncountably many complexes, in this case modules of the same sort. The compact objects in this case are the so-called what do you call it? Perfect complexes. The complexes of finite complexes of finitely generated projective modules. But you can also do the same thing here. So you might guess, that when we were working on this, that I was doing the group theory part, Srikanth was doing the commutative algebra part, but we came to some of the same thing, and this worked out pretty well. Let me end with one other thing. Okay, let's go back to the example. Okay. Let me pick a zeta where the first element is 0. The degree 1 part is 0, and the degree 0 part is 0, and the degree 1 part is not 0. Then I can write down what the m zeta is. I mean, this is sort of a very complicated piece, but it's a direct sum of copies of kh, and I'm going to index these by things that you might call u0, u1, u2, etc. Okay, so I'll index them by that. So it's a direct sum of copies of kh. So the kh action is fixed. All we have to do is say what z does, and we've got a module. If it commutes with the rest of it. And this is what you write down. You write down something like this. It's a sum of actions where in each case, on each ui, you've got a summand that goes all the way back to u0. So again, this expression gets longer and longer as I gets bigger, but still that's it. And you can show, by just tweaking the previous arguments, that there's an uncountable number of these modules that are not direct summands of any of these for m finitely generated. Okay, uncountable number. Here's the problem, and here's what's sort of unsatisfying about this. I cannot tell you, I could not pick out a set of, it'd be a matter of picking out these coefficients. I cannot pick out a set of those cohomology elements where I know that this is not in the image of the finitely generated stuff. So what we've got is we know that there is stuff that's not in there because we've got too many of them, but we don't actually know one. This seems to be sort of a hazard of the area that you can actually find yourself in this kind of predicament. But so it's sort of unsatisfying in that regard. But on the other hand, I was quite happy that we were able to get that. So I'm done. Thank you very much.
Can you say, what is the significance of a module being dualizable?
Basically, you're looking for the structure of the category, and so these are the modules for which you can do. For which you, in some sense, have a dual inside the category, and so the other part of the category, in some sense, becomes with the tensor product becomes a module over that subcategory. So that's the kind of structure that you're looking for.
So, is there any hope of doing this for arbitrary finite group schemes?
Probably, yeah.
Or you're gonna
I
need,
think so. I mean, you know, it would be, I'm not sure exactly how you would, I mean, we have the advantage in this case that,
you're going down the elementary field.
yeah, you get down to the elementary field, it probably works for elementary, for finite group schemes.
Usually there's a lot more technicalities involving
Well,
pipelines and other
okay,
things.
but what I think is that by some sort of induction process,
Uh-huh.
that you really only need to be able to find one elementary abelian P group in there
Uh-huh.
that has this property,
Right.
that has the uncountable number. And then you just induce up from that.
Yeah, though it's not, they're not always very natural.
It's not, I'm not sure how the induction works. I mean, actually, that's actually the argument we use to get that remark.
So
that I
like
just
with
said.
pi points, I mean, they're not very natural, so that's what I'm kind of worried about. So,
Yeah,
yeah. For the Lie algebra case, it's probably okay, but in general, I think it's
I don't
much
know.
more
It could
difficult.
probably be done. I think, I would be optimistic.
Okay.
I'm not sure whether you can do this in the generality of the category theory. I mean, this is what I'm not sure
Uh-huh.
about. We seem to need to actually be able to get our hands on something.
Right.
Yeah.
So you're using, at least a little bit, that you can understand these localization and co-localization functors in terms of tensoring with an object in the category.
Right.
Can you do this for any tensor triangulated category?
I don't
Or is
think
it
so.
special
I
to?
don't think so. I think that's a word. I think that's a word. Yeah. I don't think it works quite as easily.
But if you look at,
But I mean, we're also using the fact that we sort of know what these functors are.
right, so I think Benson, Iyengar, and Carlson have this set up where they have a lot of these properties when you have this kind of map into the center of the category.